Crash Course Instrumentation, Episode 15, Maximum Power Transfer and Real Source Resistance. Introduction. What if I told you that getting the most power out of a source doesn't always mean maximizing efficiency? Welcome back to Crash Course Instrumentation. In today's episode, we'll explore the Maximum Power Transfer Theorem and the often overlooked role of internal resistance in real-world sources. Internal resistance, hidden but real. Every real voltage source, batteries, generators, transmitters, has an internal resistance. It acts like an invisible resistor in series with the output. Think about a 12-volt battery. Under heavy load, the output voltage drops. That's the internal resistance at work. It consumes part of the power before it even leaves the source. Maximum power transfer, the core idea. The maximum power transfer theorem says, to get the most power into a load, the load resistance must equal the internal resistance of the source. In plain terms, if your source has 10 ohms of internal resistance, you'll deliver maximum power when your load is also 10 ohms. But here's the trade-off. When this condition is met, half of the power is wasted in the source's internal resistance. Only half reaches the load. Power versus efficiency, a balancing act. Most of the time, we don't want maximum power. We want maximum efficiency. That means we want the load resistance to be much greater than the internal resistance. Real-world example, power transmission lines. Utilities aim to minimize internal resistance to reduce voltage drop and energy loss, not match it. So, max power, max efficiency. Engineers choose based on the goal of the system. Examples in practice. Audio amplifiers. Analog designs often match speaker impedance to maximize power, but this can generate unwanted heat. Battery-powered devices. Matching internal resistance would drain the battery rapidly. Instead, we prioritize energy efficiency. Solar panels. Inverters use MPPT, maximum power point tracking, to adjust load resistance and deliver the most usable energy, an advanced version of this principle. The math, in plain English. Here's a simple way to understand the equation for power delivered to a load. Power equals the square of the source voltage times the load resistance, divided by the square of the total resistance. Or, more clearly, power equals source voltage to X load resistance, internal resistance plus load resistance. 2. Try it with different values. When the load equals the internal resistance, you'll get the highest power value. Looking ahead. Impedance, matching teaser. This idea of matching doesn't end here. In AC systems, it becomes impedance matching, a complex but essential topic in radio, communication, and instrumentation systems. We'll explore that in a future series, but for now, just remember, resistance matching is the DC version. Impedance matching is its cousin in the AC world. Wrap up. Key points to remember. Real sources have internal resistance. Maximum power happens when load equals that resistance. Sufficiency is usually more important than maximum power. This principle shows up in audio, solar, battery systems, and more. Next time, we'll wrap up this series with real-world source load models and a quick review of what we've learned. Like, share, and subscribe to stay current with Crash Course Instrumentation.